Hey there, AP2. The purpose of this video is to continue our discussion of pressure and buoyancy. We went through things a little bit fast the other day, so I want to make sure that you have all the tools you need to be successful in tonight's homework and the second assignment, Archimedes review. So you've got a couple assignments to do today. I am not there, and so you'll have this video to watch with should kind of tie everything together and give you again the tools you need to successfully complete those problems. So what did we talk about the other day? We talked about pressure, we talked about buoyancy. Some equations, P equals F over A. This is a great relationship for pressure in pascals, force in newtons, and of course area. And that's the area that in meters squared that the pressure is acting upon or the force is acting on to achieve a certain pressure. But what this equation allows us to do is find either the pressure or the force given the other variable. A lot of times we know the area that's acting upon something, maybe a solid block. The force might be its own weight, and that area might be the area in contact with the table. Like if you took a textbook and you put it on different ends, you might achieve with the same force different pressures as the surface area in contact changes. So this equation is really great for solids, where I actually know the weight of the object. Well, we can also use it within liquids too. If we know a specific pressure, we actually could find the force acting on maybe a submarine window. At some depth, there's a certain pressure. What force is acting on an area of maybe a sub window, or even the area within your ear, near your eardrum. So we can find the force acting on those things given the pressure at that depth and the area. Another equation that we used the other day was pressure equals P naught plus rho GH. So this guy again is density. This is acceleration due to gravity, 9.8. This is the depth, or really it's the height of the column of water above you. And this is atmospheric pressure at sea level. Now, to help you with your homework, this equation can be manipulated a bit. What if I have something floating on top of the water, for instance, or multiple different fluids where one's on top of the other? You know, you've all seen in that chemistry textbook somewhere where there's, you know, this fluid floating on top of this fluid, floating on top of this fluid. They've separated out by density from least to greatest. Well, as long as you're open to the air for absolute pressure, see, absolute pressure is all of it. Absolute includes the 100,000. If I just want gauge pressure, it's just the rho GH part. Okay, gauge pressure is the rho GH, assuming there's already 100,000 pascals in my gauge or whatever my device is that I'm measuring the pressure at that depth. But what if I had multiple fluids? I could actually, for absolute pressure, just add in some more rho GHs. And I could go on and on and on for first fluid, second fluid, and so on. Some keys to help you here. If you had a fluid like this, say it's open to the atmosphere up here, so that'd be P naught. What would be the pressure maybe within this fluid and the pressure inside this fluid? So what about like pressure at A or pressure at B? Given this is the density of A and this is the density of B here, it's open to pressure. Well, we'll call this H1 and H2. My pressure at A, absolute pressure, would be P naught plus rho GH of A, and that's it. I want to make sure that H1, or we'll call it HA, HB. So that height of A in meters, so if it's 20 centimeters, 0.2, would give me the absolute pressure at point A. Now, if I want to go down to point B, I could actually take the pressure at A I just calculated and just add in the rho GH for B. This height is not additive, right? So since I've already accounted for the pressure down to A, I would only need to include the H of B, the height of that B, where that density corresponds to that specific height. Any students that have taken honors last year can definitely help with this concept. We don't continue to add all the heights together each time. We do them this density with this height, this density, this height, and they have to match up. And that kind of makes sense, right? So the pressure at B, I could do as one big equation, P naught plus rho GH of A plus rho GH of B. Or if I already knew the pressure at A, I could just add to B. And that gives me the pressure. Now, what's cool about that then is if I wanted to find, say, the pressure on a sheet, or the force acting on maybe a sheet of paper at that point, or whatever it is, once I know the pressure at some point, I could then go back and plug it into this guy, given the area of that, and I could find the force acting on maybe one surface of that paper, or one side of a cube, or other shaped object. And we're gonna do some other examples with that, because I know that if the paper had thickness, the pressure is changing. But if it's a thin sheet of paper, we can just talk about the force acting maybe on one side of that sheet of paper for now. We'll go into a little bit more in depth on that. So there's some good things. You have pressure with depth, which is great for liquids where I'm just going down in a certain liquid and I'm not worried about force or area for this. I'm just looking at the pressure from the column of water above me. And then I've also got this other one that I can use for solids, or I can find the force acting on something if I know a pressure from the other equation. Cool? Okay, so this really is our pressure piece, and it was kind of where we left off the other day. We finished with Pascal's discussion of pressure with depth, pressure on solids. Where we began the other day was actually in Archimedes' principle, and Archimedes has to do with buoyancy. So let's go back to buoyancy. Buoyancy, for your understanding of physics, is really all about forces. And ideally, in buoyancy, your net force, I suppose, is zero, right? So like for the oar of the sea is a big, massive ship. You want any forces down to equal any forces up. So it really comes down to something as simple as, like a box hanging from a string. If I have a box hanging from a string, what do I know? I know that force down, force of gravity, equals the force of tension up. And those are equal and opposite. Or even a person standing on the floor. As they stand on the floor, force gravity equals force normal, right? And so buoyancy is very, very similar. Now, it's not a normal force in terms of perpendicular, I suppose. It's always up, and it's not, tension, but it is a force helping to support the object. And that force we get from an equation, force buoyancy, equals rho GV. So rho GH is the pressure piece. Rho GV is my force piece. And you can see how, if I had rho GH times area, I would end up with volume anyway. So it's kind of interesting because that would be pressure times area, right? Which is force. So rho GV, and that's the volume of fluid displaced. So if it's a helium balloon in air, I use air for the fluid displaced. If it's something in water, then I would use the water displaced. So we did an example the other day of the beach ball. What if I had to do something like, what about this? What if I had a beach ball here and it had a mass of 80 grams and it has a diameter of 8 centimeters. And I wanted to say, what's the net force on this as it's submerged in fresh water? So if it's submerged in fresh water, where my density equals 1,000, what's the net force acting on that? So we just looked at the buoyant force the other day. Well, what would be the net force? Well, net force means the sum of all forces. If you're fairly new to physics, it's where we look at all the forces acting on an object from the outside and see what kind of is unbalanced or left over. So we always know that gravity is acting on an object, but since it's submerged, we also have this buoyant force. And so the buoyant force here, which I then could eventually set it equal to ma, but I'm going to get the net force not by ma because I don't know the acceleration, simply by looking at my force diagram. My force of gravity would be 0.08. That's this piece, the grams, 3 to the left, times 9.8. And my buoyant force would be rho GV, which would be 1,000 times 9.8 times 4/3 pi r cubed. Ooh, r, I gotta be careful. R would be 4 centimeters, and that'd be 0.04 cubed. Be really careful with units in this chapter, as if you don't convert 2 decimal places and then cube it. It can get tricky really quick. Okay, so get away from you anyway. So there you go. So there's my buoyant force, and there's my weight. And if I take the difference in the two, see who wins, that'd be my net force. And I could easily set that equal to MA to then find my initial acceleration upward, which would change pretty quick because you get into drag forces, drag force, and that change, or you hit a terminal velocity pretty quick. But what would be the initial acceleration? I could take the difference. Most likely this guy's going to be bigger, but if you're ever not sure, just do the math. You guys, here's the physics. You do the math, you got a calculator. See which number is bigger. And if that blue number, the rho GV is bigger, then it's going to want to accelerate upward. If FG was bigger, then it just want to accelerate downward. But that's how you could find net force. That's how you could find buoyant force. And of course, that's how you could find weight. Cool. Okay, so let's take buoyancy a little bit further. You might have a problem where you've got a raft or a barge. Okay, so let's do this one together. So my raft is going to have a mass of, let's say, 2 kilograms. Pretty heavy raft, I suppose. Most rafts are really, really light, right? And I'm going to put a child on there with a mass of, let's say 40 kilograms. Okay. And this raft is going to be, let's do 70 centimeters long and 25 centimeters wide with a height of 10 centimeters. Okay, and the question for one like this would be, and this is what we really want to know, like when we're designing a ship, based on how heavy it's going to be, where's that water line going to be? Like when I finally do flood the dry dock with my $1 billion ship, how far is the water going to rise? I don't want it to go past that black line or blue line that you often see at the bottom of the ship. That'd be a bit of a mistake, or past the first deck, right? So what we have is a calculation that'll help us figure out, okay, where exactly is that water line going to be based on our weight and the size of the bottom of the ship. We know that we have to displace as much water, weight of water, as we have weight of ship, or mass of water as we have mass of ship. And so the question is here, like, where's that water line? That's a cool, kind of a neat application of this equation for buoyancy. We kind of see this in an older movie, Titanic. And Titanic, there's a kind of a neat scene with the engineers, if I recall. I think it was 1997, maybe, or 98 that came out. Been quite a while. But in Titanic with Leonardo DiCaprio, there's a point where the engineers are getting together and they're calculating, we can handle water in this deck, this deck, this deck. But if we get past this deck, we're sunk. There's no chance. We know that a ship, or a raft in this case, as we try to push the raft down, we know that the ship or the raft, as it goes, sinks further and further, it actually becomes more buoyant, right? It's displacing more fluid. But there is a point where the raft can no longer displace any more fluid. And at that point, a penny might make it sink. Because at that moment, once I get enough weight on it to where it's fully submerged, just the top's about to go under, it can't provide any more buoyant force. So if I've gotten to that point where the raft is just about to go under, at that point, anything else, and it goes all the way to the bottom, the buoyant force doesn't increase with depth. The pressure does. But we're going to talk about how the pressure on top and the pressure on bottom increase at the same rate. And that becomes an issue. But for this problem, what we're looking at is, what's that water line? How deep is this going to be? So what can we do? Well, like anything in physics, we're going to make it up. We're going to look at our forces. I've got the force of gravity, and I've got force buoyancy. It's really pretty simple. And ideally, those two equal, right? So as long as the raft is floating, not sinking to the bottom, then those two equal. So I can create an equation that just says, hey, FB up must equal FG down. Cool. Now what? Well, let's let it play out and see what happens. Let's see what I know about these two equations. This guy is rho GV. I'm not worried about pressure right now. This is all about just force. When you're doing these buoyancy things, you're really looking at force up versus force down. And this is going to be mg. So if I go over here, say it's a freshwater pool, or a lake or something versus saltwater. Do be careful with your density, but this would be 1,000. That's what I'm displacing, 9.8. And now my volume is not 4/3 pi r cubed, but it's going to be the raft volume. So that would be what, 0.7 is 70. So I got to be really careful with my units again, right? So 0.7, 0.25 is my width, and 0.1 is my height. And now the mass of the kid, I gotta be a little careful over here. This mass is gonna be 40. Be careful if you have grams, right? Make sure grams 3 to the left, but 40 kilograms is good, plus 2 kilograms. So kilogram is good. Kilogram is smiley face there. And then times 9.8. Oof, I don't have an equation. I mean, there's an equal sign there, but the left side doesn't equal the right side. So it's not equal, it's not an equation. So what's my problem? And some of you guys that have had honors before and maybe know a little bit about fluids are saying, oh, Richardville, you're putting too much stuff in. There's no variable to solve for. Well, there's a problem with my equation. And the problem is I'm making kind of a bold assumption. And the assumption is that I've submerged it all the way to this point. See, we have to, before we start plugging and chugging in physics, one of the biggest lessons is to think about what we're trying to accomplish. Well, for the boat, I know the whole area is in contact, but I can't assume that the entire height of it's in contact. You think of a large ship, the height's not in contact, but the whole bottom area is for the most part. Now, why do I do these barges or rafts? Because the volume's easy to calculate, as is the bottom area. If you had a V bottom boat, a real steep V, then the area in contact gets tricky as we began to sink. And so for the sake of focusing on the physics and not so much the calculus or whatever we need to get into some weird area, we can just talk about rectangular rafts or rectangular barges, some easier shapes to where our really focus is just on the physics and not so much a weird volume or area calculation. Makes sense? So, but my point is that I should have left this out. I needed a variable to solve for. The question is, how far does it sink into the water? Well, it's not displacing its entire volume. It is displacing a certain area, but not the total height. So it's that height that I'm actually going to solve for. And some of you guys might have figured that out. So at this point, you could probably cancel out the gravity here, but you could go ahead and divide, take the 42, divide all this mess over. If you do that, leave the 9.81 in and solve for h. Okay, I do the physics, you do the math. And you should get a height. Here's the deal. If I get a height of like 0.03, that seems kind of scary. 0.03, is that right? Well, remember, my goal is between 0 and 0.1. So 0.03 sounds small, but that's doable, right? So I always want to make sure in physics, does my answer make sense? Is what I'm trying to do make sense? Does that make sense? And so if I get a really small number, I want to say, oh, does that right? But actually in this case, that would be just fine. Okay. So good. Let me see what else here we might need to help you out with to make you successful in these things. Well, goodness, I don't think I need to do anything else. I think that's enough to help you out in both of these.